Welcome to solverfy.
So we have a solid metal sphere of which has a charge of minus 5.5 microcoulombs. We want to find the electric field at a different set of distances, first being 0.250 meters. Now, let's look at this case first. Because this is a metal sphere, all of its charge will be residing on the surface. And because it's a metal, the field inside would be 0. Hence, inside, for any distance less than 3 meters from the center, the field will be 0 in this whole region. So 0.250 meters is inside the sphere, and hence electric field will be 0. For part B, we are looking at 2.90 meters, which is somewhere here, which is still within the sphere, and hence the electric field is 0. But for part C, the distance is 3.1 meters, which is outside the sphere. Now, there is another thing to note. Spherical charge distributions act as if the whole charge was concentrated at the center for objects outside the sphere. That is, at this point, it will be as if the whole charge of minus 5.5 microcoulomb was concentrated at this center. Hence, the electric field would be simply Q by 4 pi r square epsilon naught, just like a point charge. But notice that we are simply finding the magnitude of charge. The direction will simply be radial, that is, in this direction, towards the center of the sphere. So the magnitude will be, charge will be 5.5 into 10 power 6 coulombs. There is another pi here, forgot the pi. Now, 1 by 4 pi epsilon naught has the value of 8.988 into 10 power 9 Newton meter square per coulomb square, if you remember, divided by r square is 3.1 meter square. This gives us 5,140, and notice the units. We lose a coulomb here, meter square there, and the units are Newton per coulomb, as we expect for electric field. Similarly, for part D, we are looking at distance 8 meters. So again, it's as if we have a charge of minus 5.5 microcoulombs, and at 8 meters distance, we are finding the electric field. So the electric field is again simply Q by 4 pi epsilon naught r square. The charge is again 5.5 into 10 power minus 6. 1 by 4 pi epsilon naught has the value of 8.988 into 10 power 9 Newton meter square per coulomb square, divided by 8 meters squared. This gives us 772 Newton per coulomb. In fact, you need not have done this. Now that you know this is 5,140 at 3.1 meters, we know that here we divided by 3.1 squared. To get the field at 8 meters, we would have to divide instead by 8 squared. So you could simply multiply this by 3.1 by 8 whole squared, and you would have the same answer. Now for part E, we want to consider what happens if it was a thin metal shell instead. The answer is nothing else, nothing different. Even if it was a thin metal spherical shell, the charge would still be on the outside, and the field inside would still be 0, and hence all the values would be the same. But the next part is a little interesting. What would happen if the sphere had constant charge density, something like a dielectric on which the charge has been put into? Now for this problem, obviously for any point outside the sphere, it is still the same. It's not obvious, by the way. It has you need to use Gauss law to figure out that for any point outside the sphere, the field will be as if the whole charge is at the center of the sphere. But for points inside the sphere, we have a formula that looks like this. 1 by 4 by epsilon naught q by r naught cube r, where r naught is the radius of the sphere and r is the distance at which we are finding the field. This is very easy to derive actually. Let's say this is r naught. Let's say we are finding at radius r. We would consider a Gaussian surface, a spherical Gaussian surface. The charge that is outside the sphere would not affect the field at point r. So only the charge that is inside the sphere would affect it. So if, let's say, the total charge density would be q by 4 by 3 pi r cubed, because the r naught cubed, because the charge is uniformly distributed. So on this Gaussian surface, we can see that the flux would be electric field times area, and the area would be 4 pi r squared. But this is equal to q by epsilon naught, where q is the enclosed charge. The enclosed charge would be rho times the enclosed volume, which is 4 by 3 pi r cubed divided by epsilon naught. Now we simply cancel the 4 pi and we have an r here. This gives us E is equal to rho by 3 epsilon naught. Now using the formula for rho, we have rho equal to q by 4 by 3 pi r naught cubed into 3 epsilon naught into r. I'm sorry, I forgot this r here. There's an r. You can see that this is the same as this formula. That's it. So for the parts C and D, the field would be the same, but for parts A and B, it would be different. For part A, where we had to find the field at distance 0.25 meters, we'll use the formula. Electric field, as we saw, was 1 by 4 by epsilon naught q by r naught cube into r. So that is, we know that 1 by 4 by epsilon naught is 8.988 into 10 power 9. Q is 5.5 into 10 power minus 6. By r naught, as we know, is 3 meters. So r naught cubed is 3 cubed times r is 0.25. This gives us 458 Newton per coulomb. And similarly, for distance 2.9 meters, we use the same formula, giving us 1 by 4 by epsilon naught is 8.988 into 10 power 9. Q is 5.5 into 10 power minus 6 by 3 cubed, but the distance is 2.9 instead, giving us 5,310 Newton per coulomb. The other two distances, 3.1 meters and 8 meters, will be the same. That's it.